In this video and the next, our focus shifts to linear systems. In this one, we'll look at linear continuous systems in finite dimensions. And in the next, we'll look at linear discrete systems and stability theory. Okay, so let's look at linear continuous systems in finite dimensions. Okay, so linear continuous systems in finite dimensions. The goal here is to see full qualitative and algebraic classification of linear continuous time systems using eigenvalues, matrix exponentials, and Jordan normal forms. And we study systems of the form dx dt equals ax, where x of t is n-dimensional, and A is a matrix that is of the n by n type in real number system. Interestingly, this looks a whole lot like one of the some of the videos under the linear algebra playlist. So, in case you want to have deeper understanding of some of the things, in case you don't get the kind of depth you want here, you can then check the linear algebra playlist, where I had taught things about linear systems and I had gone to some depths about some of these things. Okay, so let's look at the introduction. We see that a linear continuous time system has the form dx dt equals ax. In another form, we can say x dot equals ax, where x of t is n-dimensional and A is a constant matrix, an n by n matrix. So these systems are linear, of course, as you can see, and they are time invariant. They don't depend on time. That's why we say they are autonomous. Okay, yeah, that's why they are autonomous. And our goal is to classify all such systems in finite dimensions. And then we go on to linear systems and matrix flows. So the solution defines a flow. So when you solve the solution to this kind of problem, right? It defines a kind of flow. So the solution defines a flow such that phi t of x naught results to x t, like that, which satisfies the fact that after some time, we have the interaction of time and space together. So thus, solutions form a one parameter group of linear maps, right? I mean, the deal here is this. Imagine that you have x dot, x dot equals ax. That's more like dx dt equals ax. I mean, I've done this a couple of times. So we can solve this by separation of variables. So we can just have 1 over x dx, and then we have a dt, like that. And then we have integral of 1 over x dx, and we have a is constant, dt, like that. So we have ln x equals at, if you like. So, of course, with a particular constant k, like this. So if you can now take the exponent of this so that you can get rid of this now, okay? So we have e raised power ln x, and that is equal to e raised power at plus k. So that means that this is x equals e raised power at, then e raised power k here. So then we have x is equal to, if you like, some c e raised power at. So now this is the general solution, and depending on whatever c is, you can have different particular solutions. So if you actually have a particular initial point, x naught equals x of 0 equals x naught, then that simply means that at time t equals 0, x is actually x naught. So if that is the case, you can then say, of course, if you rewrite this now, x is the same thing as x of t, and that is equal to c e raised power at, like this. So you can then have x of t now. So you have x of 0 equals c e a 0. Okay, that means x of 0 is equal to c is equal to the constant. Okay, interestingly, x of 0 is x naught. This, yeah, x of 0 is x naught in short. So c now is equal to x naught. So with that in place, now we get a particular solution. So we can say therefore x is equal to, now that c is a x naught, then we have x equals x naught into e raised power at, because this is a matrix, or in more robust form, you can just say x of t is x naught e raised power at. So this goes like that, depending on whatever the initial condition is. Now that's what is actually playing out in all of this place. So imagine with a diagonal system. So you have you consider a diagonal system 1, 0, 0 minus 2. So the system is like this. You have x1 dot, that's dx1 dt is x1, dx2 dt is minus 2x2. So if you form a matrix based on this now, if you differentiate x1 with respect to x1, you get 1. With respect to x2, you get 0. For x2 now, if you differentiate with respect to x1, you get 0 because it doesn't contain x1. With respect to x2, you get minus 2. And because it's a triangular matrix now, right, or diagonal matrix in a manner of speaking, so you can say 1 and minus 2 are like these are the eigenvalues from what we learned in linear algebra. So you can then have the solution x1 of t to be c1 e raised power t, and x2 is c2 e raised power minus 2t. Now, this is exponential, it's exploding, and this is actually what's that thing called now? It's approaching zero. It's decaying. Yeah. So exponential growth and this is decay growth. This is growth and this is decay in simpler words. So we can actually represent that, using Python. So you see the solutions exponents e raised power t and e raised power minus 2t right here. So we can visualize these two curves like this. So you can see this is the exponential one that is growing because it's c e raised power t. So it's blowing up, whereas the other one is going down like this. So you have this coming down like that. So that's that about when you have a diagonal system. Going forward, we can talk about matrix exponential. Okay, matrix exponential. We also talked a lot about this under the linear algebra playlist. You want to check that out. So the general solution for just like what I showed here is x of t is e raised power 80 x naught. Same thing as this now. So x of t equals x naught e raised power 80 or e raised power 80 times x naught like we have on this page right here. So the definition of this now is that this e raised power 80 is simply the summation from k equals 0 to infinity of 80 power k all over k factorial. That's how you define e raised power 80. And this is the matrix exponential. This is what we call the matrix exponential now. So, that it basically follows the idea. It follows the same system like when you have e raised power x, and that is starts with 1 plus x plus x raised power 2 all over 2 factorial plus x raised power 3 all over 3 factorial plus x raised power 4 all over 4 factorial and so on and so forth. So it's the same thing like when you have e raised power 80. So that's simply, this is just like e raised power. This is actually 80 raised power 0 over 0 factorial plus plus up. I mean, if you follow that formula, right, it's summation from k equals 0 to, is it n now? You know, it's the same, exactly the same thing. To infinity, 80k over k factorial, exactly. So this now to infinity, okay? So to infinity, 80 raised power k over k factorial. So if you expand this now, you get for k equals 0, you have 80 raised power 0 over 0 factorial, 80 raised power 1 over 1 factorial, 80 raised power 2 over 2 factorial, 80 raised power 3 over 3 factorial, plus 80 raised power 4 over 4 factorial, and so on and so forth. So if you tidy that up, right, 80 raised power 0 is 1. 0 factorial is also 1. So this is 1. This is 80 plus 80 squared all over 2 factorial plus 80 raised power 3 all over 3 factorial and so on and so forth. So you see, it's just like that exponential expression. So this is why we called it matrix exponential. Like that is the matrix exponential. So what are some properties of the matrix exponential include the following. You have important identities like e raised power 0 is the identity matrix since you are dealing with matrices, because the identity matrix is analogous to 1 in matrix form. Then e raised power a into t plus s, following the law of indices. So this is e raised power 80 times e raised power as. Then e raised power 80 raised power minus 1 is the same thing as e raised power minus 80, Then e raised power PAP inverse t is PEAT P inverse, basically. So those are some very nice properties of matrix exponential. Then we also have diagonal matrices now. So for a diagonal matrix, A equals lambda 1, lambda 2, lambda n. So of course that simply means that when we talk about diagonal matrix, we say that um, if a matrix A is diag lambda 1, lambda 2, all the way to lambda n, we say that it's actually like this. You have lambda 1, 0, 0 up to, all some 0 down there. Then 0, lambda 2, 0 all the way down to some 0. Then and it keeps going like that until you get to some lambda n here. That's what this talks about. You have all the 0 all the way down, like that. So that's what a diagonal matrix is about. So if you have a diagonal matrix like that, then e raised power 8 is also the diagonal of the exponential of lambda 1 multiplied by t along the diagonal like that. So if you have a like this, then EAT is also like that. So if you have this, then e raised power 80 is also e raised power lambda 1 t 0 0 all the way down to 0, then 0 e raised power lambda 2 t 0 all the way down to 0, and then you have all that, you have all this now going all the way down, then this going all the way down to e raised power lambda n t like that. So that actually works. So more information on check the linear algebra playlist. So in this case now, I mean, this is a diagonal matrix, so it's 2 0 0 minus 1, so you can run this, and then you have the exponential matrix form. So the exponential matrix form of this now is simply, this is e raised power lambda 2, e raised power lambda 2. So if you take time to be 1 now, this is exponent 2, and this is exponent minus 1, basically. I mean, we can check that, right? E raised power 2, we know that to be that e raised power 2, that's 7.3. Then we have e raised power minus 1, e raised power minus 1, it's 0.36, and that's exactly what we have here. So exponential matrix of 8t now. If you take t to be 1, if you take t to be something else, you get another value also. Okay? Then we have the Jordan form. So for the Jordan form now, every matrix can be written as PJP inverse, where J is in the Jordan normal form. So of course, for diagonal matrices too, right? We can actually write every matrix as PDP inverse, where D is the diagonal matrix. And of course, P is the matrix containing the eigenvectors of the matrix. So this Jordan normal form now generalizes the idea of diagonalization, which helps to do some computations with matrices more easily. So imagine the Jordan block here. So a Jordan block has form. So instead of being just a diagonal matrix, you then have 1, 1 here, and it represents a defective eigenvalue. And this is what happens for matrices that cannot be diagonalized. You use the Jordan form instead of the regular diagonalization. So in Jordan form, right, D is just the eigenvalues along the principal diagonal without this one. But in Jordan form, now you have this one attached representing defective eigenvalues. So from that now we can talk about the exponential of a Jordan block. So if the Jordan matrix, as we have it, a Jordan block has this form. So for that Jordan block can then be written as lambda I plus n, right? With n raised power k equals 0. Okay. Then we say that e raised power jt, this j now is equal to e raised power lambda it, all right, plus e raised power nt. So, and then we say that e raised power nt, following the exponential thing, we have the initial condition. Okay, I mean, I should have done this here. This instead of writing 1 here, because we're dealing with matrix, this it should actually be the unit matrix corresponding with the dimension of the matrix we might be relating with in that instance, like that. So in this case, now this produces polynomial factors, as we can see, like as also demonstrated the other time. So imagine if you have this now, you have 1 1 0 1. Okay. So instead of having the regular, so this case now, if you had to we have 1 1 0 1, right? Like you have something like this. you have 1, 1, 0, 1. Normally, uh, if we are dealing with diagonal matrix, we should just have 0 here. But because we have this in the Jordan form, we have 1 here to show defective eigenvalue. So that's why we have that 1 there. But if we have 3 by 3, so I mean, it's just like if you have 4 by 4 also. Let's say you have 5, 0, 0, 0, 3. Okay, I mean, 0, 2, 0, 0 normally, then 0, 0, minus 3, 1. I mean, minus 3, 0 for sure. And then this is 0, 0, 0, 2, like this now. So, um, these three for Jordan form, now this is what you should have normally, right? This is what you should have normally if the matrix is diagonalizable. But if it is not diagonalizable in Jordan form now, you now have 1, 1, 1 here to make up for that. And then if you calculate the exponential matrix, you can then get the results you need to get like this. But because it's a 2 by 2 matrix, it's just this one along that line there. So, and that's the kind of thing we have here for 1, 1, 0, 1. So if you calculate the exponential matrix, taking t to be 2, you get this kind of results: 7.3890, 14.7780, 73890, like that. That's the exponential matrix in that case, because you're dealing with the Jordan block. So, talking about eigenvalues and stability, I mean, we've dealt with this a couple of times. Let the lambda I be eigenvalues of A. The stability depends on the real part of the eigenvalues. So if the real part is less than 0, we have stable eigenvalues. If the real part is greater than 0, we have unstable. If the real part is equal to 0, we say it's critical, right? So, and then we have different stability types based on the real part of the eigenvalues. Okay, so here now, talking about the stability types, we have this um asymptotic we have asymptotic stability. So we have asymptotic stability if the real part of the eigenvalue is less than 0, for every I, okay? That means all eigenvalues are negative. So we have stability. Then it is unstable if there exists any I at all where the real number part of the eigenvalue is greater than 0. So it means if you have 10 eigenvalues and only one of them, has a positive real number part, then you have instability automatically. Then we also have marginal stability if you have any real number parts equal to 0 and with no Jordan blocks. So, and then we have growth estimate. So there exists C and alpha such that the absolute value of x of t is less than or equal to C e raised power at modulus, I mean, the modulus of x of t, right? Less than or equal to C e raised power at modulus x naught. So where A now is the maximum, maximum of the real number part of all the lambda i's. So that's the growth estimate of any system you may have at all, right? Now, let's talk about classification in 2 dimensions. So when we talk about classification in 2 dimensions now, we can use trace and determinants to do that. So let A is A, B, C, D, right? So the trace of A is called tau. Trace means you add the numbers along the principal diagonal, that's AD. Then the determinant is A times D minus B times C. So the eigenvalues can then be computed as lambda equals the trace plus or minus square root of trace squared minus 4 times determinant all over 2. So, but of course, there are other ways to compute the determinant. But if you want to use trace and determinant, this is how we go now. So we can get a node where, in that case now, the determinant is greater than 0 and the square of the trace is greater than 4 times the determinant. Then it is spiral if the determinant is greater than 0 and trace squared less than 4 determinant, that's a spiral. Then its center if delta is greater than 0 and tau is equal to 0. Then it is saddle if the determinant of A is less than 0. It's a saddle. Then it's a star if we have repeated lambda. In that case, we have a star. So that these are face portrait types. So if you want to use trace and determinants, but of course there are different ways. For stability, there are all kinds of ways you can go. But trace and determinant, this classification in 2 dimensions. So imagine here that we have a system like UV with we have A00X and A01X and all of these things. So that can show us the face portrait, the kind of face portrait we might be looking at there. So here now, this shows us that everything is moving towards one center. Like it's more like water is flowing into a sink like that. And that's the face portrait in this kind of case. If you're using trace and determinant like that. Then we have higher dimensional systems. So for higher dimensional systems, for n greater than 2, we have classification. The classification uses eigenvalues, Jordan blocks, and invariant subspaces. And then we can have an invariant decomposition. The space decomposes as the n-dimensional real number system equals the composition of ES, which is the stable, EU, which is the unstable, and EC, which is the center, like that. Okay, so and we have that kind of thing here. Imagine if you have this matrix minus 2 0 0 0 1 0 0 0 0 like that, I want to extract the eigenvalues. Of course, the eigenvalues are minus 2 1 0 for this because if you have a diagonal matrix, the numbers along the diagonal are the eigenvalues. And then we go on to talk about degeneracy. Okay, we made mention of some of those concepts under linear algebra, So degeneracy, we say that a matrix is defective if the geometric multiplicity is less than the algebraic multiplicity. All this were well explained under linear algebra too. Then we say solutions contain t raised power k multiplied by e raised power lambda t factors. And then we have something like resonance. In this case, we consider that x dot is equal to ax plus f of x. So resonance occurs if lambda sub k is equal to summation from m summation of all mi plus lambda I. So if lambda k is the summation of all mi multiplied by all lambda I. So for integers mi like that. So this prevents full linearization. So if resonance gets to occur. And then we have the normal form theory. So near equilibrium, right, we have that x dot is equal to ax plus n of x. And we can transform that to y dot equals jy plus r of y, where only resonant terms remain in that situation. Then we have classification procedure in this case. Then you have x dot equals ax. So the steps to do that is you compute eigenvalues, you find the Jordan form, you compute e raised power 80, you check stability, and you decompose the space. In summary, then we see that eigenvalues represent growth and decay, eigenvectors represent directions. If you want to know more about this, in fact, I've been talking about this a lot. Maybe I should actually show it to you. Go to my channel, and then on that channel you're going to find um you'll find that's the playlist before this one I'm making now. So this is linear algebra. I have 43 videos discussing different aspects of this thing. Okay, so you have all these things, all the degeneracy, you find them there, orthogonal projections, you have all kinds of things. So applications of eigenvalues and eigenvectors, diagonalization of matrices, you have everything there. So that will give you in-depth understanding, like that to understand some of these concepts here. So here, the assumption is that you already have an understanding of eigenvalues and eigenvectors, right? So eigenvalue vectors play the role. They tell us whether a system is going to grow or decay, like we saw the other time. And eigenvectors show directions. Then for Jordan blocks, we have polynomial terms. And for real parts, we have stability. Imaginary part talks about oscillations, and resonance talks about nonlinear effects. So some key takeaways from that concept, we see that all linear systems are solved by e raised power 80. Then Jordan form gives full classification. That is for systems, for systems that can, if that Jordan form is like, it works when diagonalization fails, right? And diagonalization helps to solve to make simplified matrices, especially if they are if you have a very large matrix system. Then stability depends on real parts. Then two-dimensional systems admit complete classification, like what that case of using trace and determinant. Then higher dimensions decompose. Degeneracy introduces polynomial growth, and resonance affects nonlinear behavior like that. So we have some practice problems here to try our hands on. Can I show them enthusiasts? Solve the following problems. Show all steps and justify your answers. Solve the system this with initial condition that. Of course, you're going to do it like using e raised power at like that, and then you have your initial condition right here. Then you have this also compute e raised power at for this, then find the general solution of this. So this same process we went through on the other page. Then 3 and 4. Okay, maybe I can even show 3, 4, 5 here. Same story. So here you want to do phase portraits, find eigenvalues, classify the equilibrium, describe the phase portrait. You can. So I think that was the kind of thing we did with that phase portrait. Just put the matrices, and then you have the phase portrait. Then you have 6, 7, and 8 if possible. Okay, 6, 7 can be fit into this. Oh, okay, let's just do 6, 7 so we can see everything as clearly as possible. So we have the trace determinant method. So we want to compute the trace of this, the determinant, and then you classify the equilibrium based on that table we found the other time. Then higher dimensional system, you have this find eigenvalues. The eigenvalues are straight to read, -2, 1, and -1 because this is a diagonal matrix. Then decompose R3 into ES, EU, and EC like this. So of course, because you have -2 and -2 here, this indicates stability, stability, but because there's this different one that is different, so we're going to have an unstable system for sure. So the long-term behavior is that it is unstable. Then we have defective matrix like this. Find the general solution and explain the role of the polynomial term. So this one you have here now, because it's a defective matrix, uh, so that's why we have one here. So this like Jordan form or something like that. So we have number 9 and 10 now. Numerical solution, find the eigenvalues. Okay, I mean, it's not a diagonal matrix in that sense. So you have to do the regular finding of diagonal matrix. And then we have the idea of resonance playing into this place based on the condition stated before now. Okay, let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Um, if you have subscribed already, I must say thank you very much for doing that. If you haven't subscribed, what exactly are you waiting for? Go ahead, subscribe, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That comes with some special privileges, like you get to see some videos first, or some videos are made totally for you as a member. I can consult for you on something that relates to this channel, something I can help you with uh, ethically, and so on and so forth. So ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.